Okay, so this is the last lesson in the gas laws unit, and let's finish up. So we're going to talk a little bit about water displacement, and water displacement for gases is basically when we're collecting water over a gas. So if we bubble a gas and we collect it and it goes through water, we have to correct for the fact that it's passing through water, because as it passes through, it will take some water vapor with it. So any gas that we collect, in this picture you'll see that you're collecting hydrogen, there's also some water vapor, and so we have to correct for that. Luckily, there's a data tables full of water vapor pressure at certain temperatures, so you just have to do a correction for that, and then make sure you use the dry gas. And so you correct for it, and then you call it the dry gas. Okay? So here is basically what's going on. You correct for the pipe, the pressure. We did this in Chem 1, maybe. I can't remember. Some of you may have, some of you may have not. We changed some labs up. So let's just go into working a problem so we know what to do. I didn't write this problem in the PowerPoint because it's a ginormous problem. So I am going to go ahead and write the balanced equation up here at the top so that when we're referring back to it, it's right there. So we have potassium chlorate, which is a solid, being decomposed, going back into the potassium chloride and oxygen gas. So we would be collecting that oxygen gas over water. So it gives us some information. It says we are at 22 degrees Celsius, gives us the total pressure, and it says the vapor pressure at that temperature was 21 torr. So the first thing we want to do is correct for the oxygen. So we would just take 754 minus 21. So the pressure of the gas that we collected would be 733 torr. Okay? Because they gave it to us in torr, we will not be able to leave it in torr. We're going to need to put it into atmosphere. So we are going to solve for the volume of oxygen that we collected at that pressure. So I'm going to say NO2, and of course that's going to be PV over RT. So for my P, I'm going to go ahead and just do my conversion right there in the problem to show that I know that in 760 torr are 1 atmosphere. So I'm going to go ahead and do that there. And then I'm going to say 0.65 liters because that was the amount of gas we collected. And then I'm going to do my 0.08206. And then I'm going to do 295 K, which is the temperature. So then that is going to give me 0.0259 moles of oxygen. So once I do that, then I can use my mole ratio and molar mass of potassium chlorate that was decomposed. So let's show that we're doing the next step by a new color. From the balanced equation, for every 3 moles of oxygen that was produced, there were 2 moles of potassium chlorate decomposed. The molar mass is 122.55. And we need 3 sig figs, so that would come out to be 2.12 grams of potassium chlorate was originally decomposed. Okay? So that brings us to the theory part at the end of the lesson. So we're talking about the kinetic molecular theory. The components of that are the particles are so small compared to the distance between them that the volume of individual particles can be assumed to be negligible or zero. Of course, the particles are in constant motion, and they are colliding with the walls of the container, which causes pressure, and then the particles are assumed to exert no force on each other. They are assumed to either attract or repel each other, and then the average kinetic energy is assumed to be directly proportional to the Kelvin temperature of the gas. Okay. However, in real life, real gases do not conform to these assumptions. The kinetic energy is equal to 3/2 RT. This formula is not on the AP exam. I just want you to understand it. And the units, here's what's important. The units are in joules per mole. So we use a new R value right here. Now, on the stoichiometry test, I saw some of you using that R value. We only use this R value if we are talking about energy. So that's why we use this R value and not the 0.0826. When we're dealing with pressure and volume, we're using the 0.0826. When we're dealing with energy, we're going to use the 8.34. Temperature in both cases has to be in kelvins. In reality, real gases have many collisions between particles, and the average distance between a particle, between the collision and a gas sample, is called their mean free path, and it varies based on their densities. So this is something called a Boltzmann distribution graph. You should expect to see this on a multiple choice question. So I want to explain what's going on in this graph. These are showing gases at different temperatures and what happens to their velocity. And so when their temperature is not very high, you have a whole lot of particles under this first peak. Okay? Basically, it's the same amount of particles under each peak. It's just the shape of the peak changes. And the reason it changes is as I heat them up, speed them up. So if I heat my particle, I increase my temperature, I'm going to increase my velocity. And so the graph kind of flattens out because now we have more particles going faster, and then as I heat them up it flattens out even more because I have more particles moving at faster and faster velocities. Okay, so this is going to be an important graph to understand. So here are some things that I want to add into that before, do I have room to write it? I'm going to go back. So here is something that is an important concept that a lot of students get confused in their mind. Okay, kinetic energy, I'm going to write this down. Kinetic energy is the same for any gas It's the same for any gas at the same temperature. Okay? The kinetic energy is the same for any gas at the same temperature. The velocity is not. That's speed. Okay? So in other words, this is important because people miss it all the time. If you have an increased mass, you're going to have a slower velocity. Okay? The lighter the gas, the faster the velocity. But if they're all at the same temperature, they're going to have all the same kinetic energy. So let's say I have H2, O2, and CO2. Okay? And I'm at 0 degrees Celsius, 273 K. They all have same kinetic energy. But which one of these gases is going to be moving the fastest? Meaning it has the highest velocity. And that would be hydrogen because it is the lightest gas. But hydrogen would have the same kinetic energy as the O2 particles and the CO2 particles at the same kinetic energy. But their velocities are different. So a lot of times kids get kinetic energy and velocity confused and think they're the same thing. And the reason they're different is we're going to go back to that kinetic energy is equal to 1/2 mv squared. So I apologize, the internet just cut out on me. What I was saying was we'll go back to 1/2 is mv squared, and we can see how their kinetic energy will remain the same at the same temperature, but their velocities are multiplied, velocity squared multiplied by their mass. That's how kinetic energy stays the same, but I want to make sure you understand that velocity is not the same at the same temperature. Lighter gases are going to have faster velocities, okay, which will lead us into effusion and diffusion. Okay, if you recall from Chem 1, diffusion is the mixing of gases. Okay, if I open a room and let a bunch of gas in there, they're going to mix evenly. Effusion is the passage of gas through a tiny orifice into an evacuated chamber. So it can it's basically how your tire gets a hole in it, it leaks. Okay, Graham's law of effusion says the rate is inversely proportional to the square root of the mass of the particles. Okay, so we have the rate of effusion, and you have the molar mass of the gas 2 on top, molar mass of gas 1 on bottom. These calculations are not on the AP exam. I'm showing you them, but I want you to understand so you see that it is lighter gases are obviously going to effuse and diffuse faster than heavier gases. That goes back to the fact that they have higher velocities if they're lighter, so they'll move faster. Real gases do not follow the ideal gas. No gas exactly follows the ideal gas law or all the assumptions of the kinetic molecular theory. These are behaviors that get close to ideal gas. They can approach ideal gas behavior at low pressures and high temperatures. Incidentally, students also behave most ideally under these conditions as well. Summer vacation. High temperatures, there's less interaction between particles because they're moving so fast. At high concentrations, though, gases have a much greater force of attraction because there's more particles. They're causing to hit the container more often with less force. And then high pressure or small volume, the volume of the particles become significant because they're closer together, and so they can interact more with each other. Attractive forces are greatest for large, complex molecules and polar molecules. We said that a couple of lessons ago. We can use something called van der Waals equation to adjust for those departures from ideal equations, and it looks like this. But don't worry, you're not tested on it. Doesn't mean you can't be asked a question concerning their behaviors, but so if you look at this and understand that you can correct for that. But you will not be tested on the AP exam for that, okay? And then remember that rate is a change in quantity over time, not just time, okay? All right. So lastly, I'm going to reiterate some stuff just because I want to make sure you know. Remember that at STP, we're going to use 22.4 liters per mole. Do a little happy dance when you see STP because life is easier at STP. And then, of course, if you're at non-STP conditions, you're going to use the ideal gas law. Don't be afraid. You might have to work it 3 or 4 times in 3 or 4 different parameters, just like we did in some of our examples. And then I just said it, but I can't stress it enough because these are easy give me questions on the AP exam. This is your low-hanging fruit. At the same temperature, kinetic energy of any gas is the same, but lighter gases, lower molar masses, will have a higher speed or velocity. All right, just leave you with this.